Okay, thanks everyone for joining our UCANR monthly water webinar. Today, I'm really delighted to host Dr. Thomas Harder from UC Davis. Dr. Harder holds a joint appointment as a professor and cooperative extension specialist in the Department of Land, Air, and Water Resources. And he's currently chair of the Hydrologic Science Graduate Group, as well as associate director of the Center for Watershed Sciences. Dr. Harder's research and extension emphasizes the nexus between groundwater and agriculture. His research group focuses on non-point source pollution of groundwater, sustainable groundwater management, groundwater and Vardos zone, modeling, groundwater resource evaluation under uncertainty, climate change, groundwater surface water interaction, and contaminant transport, just to list few of the expertise. And his work uses a range of numerical, statistical, and stochastic modeling approaches, often combined with the field research, to evaluate impact of agriculture on human activity on groundwater flow and contaminant transport. And he is also unofficially known as the groundwater guru of the Central Valley and throughout the world. So Thomas, take it away.
Well, I'm not sure about that part, but it's certainly fun to be playing in the groundwater world here in California. Safik, thank you for the invitation to give a presentation today and the opportunity to do so. And thank you to everybody for being here. And it's good to see some familiar faces here. I'm going to sort of use a big title for a few smaller stories, but I think those smaller stories are quite relevant to the title, Frontiers in Sustainable Management of Groundwater, where we are really in a place in California, as probably most of you know, we're pioneering that in so many ways. Before I get going, I wanted to acknowledge that much of the work in my research group I don't do. That's a lot of other people that are engaged in this work, and a couple are here. Gus is here, who's been doing work, his PhD on Siskiyou County groundwater, and I'll talk about that here in a little bit. Hani Haynes is here. She is doing her master's with me on modeling nitrate from an orchard and near an orchard, and I'll talk about that actually later as well. And Jay is here, and Jay and I, as some of you know, did the led the nitrate report to the legislature with a very large team now 10 years ago. Now, for those of you that are not dealing with groundwater on a day in and day out basis, I'm gonna provide a little bit of an outline sort of on the global importance of the groundwater agriculture nexus first, very briefly, and the context for doing science at this interface between groundwater and agriculture. And then spend much of the time on two examples that we're approaching with our work and that we're trying to tackle and highlight with our work on the groundwater supply side, and then an example on the groundwater quality side with the nitrate work that we're doing. So for those that may not have sort of thinking about water in a global context, why is this work, both the research, the teaching, and for us in cooperative extension, the outreach on groundwater at this nexus with agriculture so important? Well, water is primarily used around the world by agriculture. Agriculture is the biggest consumptive user of water. Irrigation accounts for 42%, almost 80% of water use, and groundwater itself is 42% of that irrigation water use, and 43% when you just look at the consumptive use fraction, the part that actually goes into the atmosphere. And that is a big part of the total. So worldwide, irrigation uses around 3,100 or 3,000 cubic kilometers. That's very roughly speaking, 3,000 million acre feet, 3,500 million acre feet, something like that, if I got the conversion correct. which is about 3/4 of the total water use. And if you look at the consumptive water use, it's like 80% is in irrigation, then almost half of that is from groundwater. Agricultural water use is focused on these humid to semi-arid regions and arid regions around the globe, from the North China Plain through South Asia, the Middle East, the Mediterranean, significant parts of the Midwest, and then of course the Western United States, but also parts of South America. And in many of those regions, groundwater extractions far exceeds the amount of recharge, leading to overdraft, leading to water shortages, and projections for the economic impact of that dwindling resource by the end of this century are quite dire. And we're looking at potentially moving a lot of that, well, a significant chunk, maybe not a lot, but a significant chunk of that irrigation into rain-fed agriculture. But there's also a lot of water quality implications. And so while my work and the work of those that have worked and are working in my group is very much focused on California, I have found over the past 20 years that the issues that we tackle here sort of in the microcosm of California, or even smaller microcosm of the Central Valley, or the even smaller microcosm of places like the Scott Valley with 2,000 people and 50,000 acres of irrigated lands, the issues that we encounter, both the scientific challenges as well as the issues of translating science to the people that actually manage the place, are repeated over and over again around the world. Within the European Union, in Africa and Asia, we find this very similar challenges. Perhaps the societal context is somewhat different. Perhaps the regulatory frameworks are different, but fundamentally we see very similar challenges. And so that's why it's been rather rewarding to work on these issues, even if our work has focused mostly on California. But I thought I point that out. Just because we work in California, we don't just work on California issues. We're actually addressing issues that have value around the globe. Now, this nexus between groundwater and agriculture is really sort of one nexus between the larger context of course, land use, various land uses, and natural resources. There's impacts of that land use on those resources, and then there's, of course, the extraction of those resources by the land use, and groundwater and agriculture are very similar to that. And there's a lot of topics that evolve out of this nexus, and also out of the proximity of agriculture to other land uses and the link of groundwater to other resources. I list a few topics here, and if you're interested in, we've organized a conference on this nexus now a couple times, and we'll be hopefully organizing this again within the next couple of years. And you can find a lot of interesting topics and talks at this website that I'm listing here in the lower right-hand corner. So let me start by sort of bringing up a couple examples here from on the supply side. So I roughly divide the topics that we have in this nexus into a supply side nexus, where we talk about groundwater supply and managing those supplies in ways that minimize the negative effects of dwindling supplies on one hand, and then groundwater quality on the other hand. On the supply side, California is, as far as groundwater is concerned, not doing particularly well. The supply conditions for groundwater have been becoming more and more marginal, which is not to say that we're running out of water, but we're certainly seeing changes in groundwater conditions now far beyond what we call critically overdrafted basins of the southern part of the Central Valley, well into Northern California, including some of the smaller basins in the intermontane region. And if you look at, this is the 20-year change in water levels between the year 2000 and the year 2020. It's been downward in most regions in California, and not by a small margin. And if you look at water level conditions last year, this is from DWR Sigma Data Viewer website, most wells, especially in Northern California, are in their lowest 25th percentile ever measured in the history of many of those wells. And so that's been part of the reason why we've been able to pass the Sustainable Groundwater Management Act of 2014. Without going into any details, the two things that this act does is it puts control of groundwater resources into the agency, into the hands of local agencies, so-called groundwater sustainability agencies. And really emphasizes that local control, including the stakeholder engagement in that local control, not some backroom negotiations between few people, but really a democratic stakeholder process, at least ideally. The other thing it does is it requires sustainability as the ultimate outcome of groundwater management. That's very different from, say, the state of Texas, which requires at worst, a planned depletion of groundwater. It allows for that planned depletion if basins choose so. And that's a very different outcome from what we're envisioning and what the legislature was envisioning when it passed the Sustainable Groundwater Management Act of 2014. The other piece that's unique about the Sustainable Groundwater Management Act is that it not only looks at water levels and groundwater storage, but it looks at the consequences of changing that with respect to groundwater quality and with respect to surface water. So the depletion of surface water and the impacts to groundwater dependent ecosystems play an important role in doing that local planning for groundwater sustainability. Now, these plans that are now emerging from these newly formed groundwater sustainability agencies and that are due by the end of this year, they're in some ways can be characterized as a plan to balance the needs for groundwater and groundwater protection between the need for having a healthy economy, the need for providing for healthy people, and the need for providing for a healthy environment. And that balancing act is one where policy, of course, plays an important role. I always like to, as an introduction to what it means to operate as a scientist at the interface with policy, I like to pull up this cartoon that sort of shows the primary pieces that go into policy making and into a regulatory framework. And this is, as an example, this is the speed limit. The first step to a regulation is to identify risk drivers and impacts. And in the case of the speed limit, somebody did a study a long time ago that found out that driving a car very fast causes harm to people. They then also made a determination that among the risk drivers, which are drivers, we can categorize those that operate heavy trucks versus those that drive a regular car. And I give credit to Jay educating me about the fact that we can have regulations that are rather universal, that look at causes in a universal way and regulate everybody the same, which makes it easy in some ways because you don't have to spend a lot of time distinguishing different risks versus structured approaches that can be much more costly in sort of identifying and managing individual pieces of these risk drivers, but are also much more targeted and much more effective in many ways. So with respect to the speed limit, the responsible party then is, and the party that's regulated is the driver. And so knowing who that responsible party is and any regulation identifying that's one important piece, and we will find this in all of our environmental regulations. Those responsible parties, they're given limits, and to see whether they're exceeding those limits or not, they need to have some feedback mechanisms. And in the case of the car, that's a speedometer. So having a measurement tool that measures the state of their system, in the case of the speed limit, the speed of the system, is a really important part because that tells the driver in an instant whether or not they're in good shape or not. And then in order for them to actually manage their speed, They have a management system. In the car's case, it's a brake and a gas pedal. And so having these management tools that allow the driver to control speed as she or he sees what speed they have, that's part of actually then managing that system. Enforcement is another important part. No regulation will work unless there's some fair kind of enforcement. In the case of the speed limit, those are the radar controls. Now, with the Sustainable Groundwater Management Act, who's the driver? The driver, the responsible party, is the Groundwater Sustainability Agency, but then the Groundwater Sustainability Agency, to the degree it is a regulatory agency, will have individual pumpers as the responsible parties. But let's stick to the Groundwater Sustainability Agencies. They will have and need management tools to manage their groundwater supplies and their groundwater demands, because what they're trying to do is to balance supplies. They don't want to be moving up and down, or they don't want to keep losing groundwater and moving their water table downward. And so they need some kind of monitoring mechanism. They need a speedometer. That's the monitoring in order to manage their supplies. They also need a management system that they understand in terms of the hydrology, in terms of what goes in and out of that system. How does the water level how is the water level controlled? In order to properly make decisions on the supply side or on the demand side for groundwater, this understanding of the hydrology, understanding the risk drivers and impacts is really important. And part of that is all the monitoring that we do in groundwater basins, the modeling, the assessments, et cetera, et cetera. The enforcement comes from the State Department of Water Resources and State Water Resources Control Board. Now, the first example I wanted to give you here in terms of a challenge is this speedometer piece in the context of the groundwater sustainability plans. Typically, we think of monitoring a groundwater system or any environmental system, we think of as having some kind of a meter with which we can measure whether or not we are in healthy conditions, or whether we're getting to a threshold where we have undesirable results, as the SIGMA legislation calls it. And so we have thresholds or maximum or minimum levels, and depending on your environmental legislation, they might have different names. In the context of SIGMA, we have a optimal range, which we call the measurable objective, and a threshold, which may be a minimum or maximum threshold, depending on whether we're talking about water levels or seawater intrusion, about water quality, land subsidence, or surface water depletion. And now, in that context, the local agencies, which are now very much engaged with local stakeholders that are not all, and in fact, most of them are not hydrologists or environmental scientists, have no background in it. We need to teach them about these measurement tools, and we need to convey to them that they can trust these measurement tools. And the standard process here has been to look for well-worn and well-known instruments that you can put into field to figure out whether your water levels are going down or not, whether your water quality is being degraded or not. Now, surface water depletion is a particular indicator that needs to be measured here, for which we actually do not have a tool that we can stick into the ground and measure. And so the surface water depletion part is an important part that I'm going to illustrate using Scott Valley in Siskiyou County near the Oregon border as an example. Scott Valley is a small intermontane basin just south of the Oregon border, which you have here on the horizon. And in this intermontane basin, for geologic reasons, you have the deposition of these alluvial soils and sediments that form a small aquifer system, about 20 miles wide and about 20 miles long and about 5 miles wide. And through this valley, you have the Scott River flowing through the valley, and at the northeast western edge of the valley, the river actually falls down into a gorge and flows into the Klamath River. And the Klamath River goes out to the Pacific. Because of that connection, we have, of course, as we are in California, we have salmon in this river, and that salmon depends very much on good flows in this river in the fall, but also during the summer for juvenile coho. What we also have in this valley is irrigated agriculture. And during the season when we don't have rain, irrigated agriculture pumps groundwater that they use for irrigation. And that's water that will not make it to the stream. And pumping of that groundwater has caused significant reductions in the summer base flow that's carried by the Scott River out to the ocean. The conversion from flood irrigation to drip irrigation or sprinkler irrigation, which went along with the switch from using exclusively surface water to also using groundwater, occurred in the 1970s. And as a result, we have seen much lower flows in the Scott River. This is the hydrograph for the Scott River from 1942 to 2020. And the down bump is the summer season. The up bump is our rainy winter season. And you can see that prior to the 1970s, low flows were on the order of about 40 CFS. And post 1970s, after this conversion happened, we have low flows that are on the order of 10 CFS. Now, what Gus has done, who's actually here in the audience, is he's built a relatively complex integrated hydrologic model of this system that accounts for the upper watershed, it accounts for the surface water system in here, it accounts for the soil and land use system in here, it accounts for the Vito zone, and it accounts for the groundwater system, all of which are linked together. There are essentially a lot of models coupled. You have a groundwater flow equation, you have Vito zone processes, you have a cropping system and farmer decisions, and then you have the upper watershed that provides all of the surface water supplies that flow into this valley that recharge the groundwater system and are equally important. These kind of models can get really complex, many different parameters. And so what we do with these is we build these models based on a lot of measurements, but then we also calibrate these models against measurements that we have. We calibrate these models against water level measurements that we have. Here are a number of hydrographs showing how simulated values in red match with measured values in blue, and how measured values correlate with simulated values. We want this ideally on a straight line or not scattered too far from the straight line. Here showing the network of wells for which we do have these water level measurements. We also match this model to the observed stream flows. So in blue, you have observed stream flows here at the Fort Jones Gauge, where the river flows out to the gorge. And in red, you have the simulated values. These kind of calibrations are really important, working with the stakeholders in this valley that are going to have to make decisions on how they manage their groundwater that may be rather costly to the local economy. These kind of calibrations are very important to the degree these models are used for decision-making in building trust. Trust that this model actually provides the right guidance in making decisions about groundwater management. Part of what we can look at with these integrated complex models is also we can look at stream behavior. This is a heat map showing the exchange of water between the Scott River and the groundwater aquifer along the entire length of the Scott River in the valley. So we take this entire Scott River, we stretch it into a straight line, which is the vertical axis here. And then we plot the exchange along that river in color as we proceed through time. This is a 20-year period from 1990 to 2011. And the colors indicate whether we have upflow or downflow to indicate the strength of that flow. And in white, we see times when we have essentially a dry river. So there's a lot of information that we get out of these models that complement our monitoring data, and in making sure that the model predicts what we observe relatively well. Here showing, for example, in red, all the places where the model correctly predicts that the river falls dry during August of 2001 or August 2010. That's another piece by which we build trust with the stakeholders in that the model can predict correctly what is of importance to the sustainability of this basin, one piece of which is the water level, and the other piece in the context of the depletion of surface water is how much stream flow we actually have at any given time in this stream system. So once we have built this system, then we can use this modeling system to actually do some measurements. And we do two kinds of measurements with this. And we do that with these models by actually doing multiple model runs. We have as a base model, a model that's calibrated to the historic period, in this case, 20-year period from 1991, or actually almost 30-year period now, from 1991 to 2018, with the work by Claire Cooper, who has added to Gus's work. We run this essentially for a historic period. The first question and the most important question that we're interested in the context of the Sustainable Groundwater Management Act is, how much does this groundwater pumping actually deplete stream flow during the critical low flow season in the summer and into the fall, September and October, when fall run Chinook are trying to come up in the stream, and in the summer while juvenile coho are over summering in the stream. In order to measure that, we cannot go out and measure the difference in stream flow between if we had no pumping versus now that we have pumping. There's no way to measure that difference. And so what we do is we run this model that we have calibrated for historic conditions, and replace irrigated agriculture with what would be in place if we were not able to irrigate that land, which would be some natural vegetation. And that natural vegetation has its own ET, has its own connection to groundwater. And we calculate what stream flow and stream flow distribution is in the system. We can calculate how water levels change or how water levels are different. And we compare this no pumping reference case against this base model. And because we're not pumping groundwater in this reference model, the stream flow here in the summer and the fall is significantly higher than here. And we can measure that amount in cubic feet per second for each month of this simulation model. And I'll show you an example here in a minute. The other thing that we can do with this tool is we can measure not only what the stream depletion is, but we can also measure how much of that stream depletion we can reverse by implementing projects and management actions, either reduce the amount of pumping that we're doing right now or increase the amount of recharge by implementing managed aquifer recharge projects in that basin. And so to do that, we run models for specific projects and management actions, and again compare the outcome in terms of stream flow and water levels against this historic base model. And so that allows us then, with this model, to measure the impact of that project. Now this is an interesting approach, but it's also a challenging approach, because it means there's not a meter in the river or in a well that is very obviously measuring something rather tangible. To the stakeholders, this is a model that's predicting something, and for them to believe the values that come out of this model, that perhaps indeed stream flows are depleted by 40 CFS or 50 CFS from their original values, or 30 CFS, for them to believe that, they need to be able to trust this model. This is a discussion not any different from the discussions we have about, whether or not we have climate change, which is all based on models. So we can use these models to also evaluate then recharge projects, for example. Gus has used this model to make some very interesting research findings in terms of how pumping in different parts of this valley in a wet year, in an average year, or in a dry year, in August versus September versus October, impacts the stream flow out of the valley at the Fort Jones gauge. The bigger the impact, the warmer the color here. And so it turns out that only in a wet year and only in August, there's a significant impact from pumping. In dry years, there seems to be very little impact from pumping, but that is because the stream is actually dry. So there's no impact. And the other piece that Gus has found, and that's shown in these hydrographs here, which show that impact, that it takes the reconnection of the stream to actually then translate that impact. The impact of groundwater pumping in the summer is not on stream flow in the summer. The impact of pumping in the summer is on the time when the stream reconnects and starts flowing again in the fall. And those are some important findings that then have to be translated back into understanding the value of projects and management actions on the in terms of ecosystem improvements. So using a model as part of measuring sustainability is going to be an important concept, and one where in the interactions that we have with stakeholders, we're finding this is a challenging concept to get across when it's not just a meter that we all trust and all know it works, but when this meter is actually a model that is calibrated with a lot of data, a lot of very diverse data, including research projects, and that is then measuring different projects and management actions, different scenarios in order to come up with that measurement value. Here is an example of this type of measurement with the model. We run the model for the historic scenario here in dashed line, and I'm showing here hydrographs for the Scott River in 3 years, from January through December, for a dry year in red, for an average year in orange, and for a wet year in blue. The dashed line showing the hydrograph as was actually experienced and simulated quite accurately with the model. And then in red showing the hydrograph when we have, instead of agriculture, we simulate a natural vegetation that doesn't require groundwater pumping. And that difference in flow, that is the total depletion that we're actually looking at, and some of which we're trying to revert with projects and management actions. So if we implement, for example, managed aquifer recharge, we can revert about 20% of that depletion as a result of implementing that project and management actions. And that then has some implications on the ecology. It has implications on the viability of the fish. Now, part of this modeling, and the interesting part that we can do, where Gus has spent quite some time, is we know about the variability of some of the uncertainty about the input parameters. So think of these probability distribution functions that are shown here in colorful ways as the probability distributions of our input parameters. They're not precise. They could be anywhere within that histogram, where that histogram shows the probability of any one of these values. And by using stochastic methods in this modeling, we can use this uncertain input parameters to translate model results into what is the uncertainty about our predictions. That gets to be rather complex, is very interesting from an academic perspective, but we're really challenging in translating this to stakeholders that have no technical expertise. But I think it's going to be an important piece of moving forward, and we have to find ways to be able to translate these types of uncertainty analysis to the stakeholders. We can nicely actually point out from some of these analyses that there's a relatively limited range in that uncertainty, again, helping to build trust in the modeling exercise. So that's one example. Another example that I wanted to point out is understanding these risk drivers and impacts. And how we can use our understanding helping stakeholders and regulators and policymakers better understand risk drivers and impacts. One of the common misnomers in the Sigma world is, and it's driven by the focus of Sigma on overdrafted basins, is that when water levels decline on a continuous basin, then the basin is an overdraft. What else could it be, right? Well, let's take another intermontane basin in Northern California as an example of a basin that has declining water levels, but we're questioning, or where we have to raise the question, is this really overdraft? And where some basic conceptual considerations actually lead us to find that while the basin is experiencing lowering of water levels, it's far from being an overdraft. How could that be? So the example is Butte Valley, which is about 80 miles east of Scott Valley. Scott Valley would be just to the left of this map. Here's Shasta Valley. Mount Shasta is just outside the bottom of this map. Butte Valley lies at the edge of the Modoc Plateau, which straddles the Oregon and California border. And it is part of the Klamath Basin, which is this larger basin here. This map is showing groundwater level contours, or estimated groundwater level contours. And what those groundwater level contours tell us is that the recharge that occurs here in these higher volcanics seems to be moving into groundwater, first of all. There's very little surface flow. And moving through this alluvial basin here, through the volcanics, and continuing to flow past the valley into the lower Klamath Valley, and from there into a slew of sloughs and wetlands and into the Klamath River itself. And so in the cross section, what we have is we have mountains to the south and southwest of Butte Valley. Butte Valley itself is an alluvial basin with sands and lake bed sediments. And then to the north and northeast, we have the lower Klamath Wildlife Refuge, still lower, about 80 feet lower or so, than 100 feet lower than Butte Valley. Now, the interesting thing there is that Butte Valley is surrounded by volcanic rocks, and these volcanic rocks turn out to be quite permeable, much more so than, say, the Sierra Nevada or the Coast Range. And so all of this is filled with groundwater. The recharge comes from the mountains. There is some groundwater pumping, some discharge in form of groundwater pumping here in Butte Valley, but ultimately that groundwater gets discharged into into the Klamath River and the associated wetlands. So we have a flow system from the south to the north, and we're siphoning off some of this groundwater through groundwater pumping in Butte Valley. So why would there be a declining water level if this basin is not an overdraft? Well, let's look at what drives the water level in here. The water level in here is driven by the amount of water flowing through this mountain range here and the hydraulic conductivity of this mountain range. And since that is fixed, that hydraulic conductivity, the more water you have flowing through here, the steeper the gradient has to be. And so that would, if you have more water flowing through here, that would raise the water table. If you have less water flowing through here, it would lower the slope of this water table, and you would have a lower water level in here. Now, why would this flow of water be more or less? Well, one of the things that we see in Northern California, Southern Oregon, is that we've had a precipitous decline in precipitation over the last 20 years. This is the precipitation record from 1940 to 2020. This is the last 20 years here. We also see, this is the declining water levels that coincide with these last 20 years of decreased precipitation. Some declines in the 1977 drought, some declines in the early 1990s drought, of which we recovered most, but not all. And then huge declines in the last 20 years that only recently have stabilized. Now, less precipitation means that the recharge over here is going to be significantly less, which means less water is flowing in here, but the same amount of water is coming out here. And so as a result, with less coming in and the same amount coming out here, while it's not overdraft, there's less water going through this mountain range, which then leads to a lower slope of this water table. And that lowers the water table in Butte Valley. The other thing that we're seeing is that actually pumping increased. So over the past 20 years, we've seen about a 10 to 20% increase in groundwater pumping and consumptive use. And so by pumping more out of here, that's another way we reduce the amount of water that is left over to move out to the Klamath system. And so less pumping, more water going out to the right, more pumping, less water going out to the right, and therefore a shallower gradient and lower water tables in Butte Valley. Moving forward, therefore, out of these considerations, we can say that if we don't have climate change, then keeping the current rate of extraction should completely stabilize the water table, because we're not changing anything in the overall flow system. And so we should actually be rather stable. And that in turn then informs where we're setting minimum thresholds and where we think we ought to be in terms of future water levels, which are two requirements under Sigma. We have to identify our optimal range and our minimum threshold for water levels. To the degree that we might experience climate change, that leads to less recharge. And we don't know exactly whether climate change indeed leads to less recharge. That's an open question. But if it was to lead to less recharge, even if we don't change groundwater pumping, that climate change then leads to a lowering of water levels, which would force the agency to shut down groundwater pumping in Butte Valley. The undesirable result in Butte Valley specifically is primarily domestic wells and public water supply wells going dry. Avoiding that undesirable result, one way to avoid some of those undesirable results is by creating some funds that can help actually deepening water levels to those most shallow wells that would fall dry. And so besides keeping groundwater pumping from expanding in the valley, another management action that we're looking at is some kind of funding mechanisms to essentially pay out well outages and allow them to drill deeper wells. So this is an example of a conceptual model that is also confirmed through a groundwater model that Andrew Calderwood is developing right now, and showing that in fact under both drier and wetter future climate conditions, the long-term outlook for this basin is that it can keep water levels stable, and depending on whether it's dry or wetter, either at a higher level or at a lower level. This is relevant to much of Northern California. Again, we're in a drought this year. We've had an accumulation of droughts over the past 20 years. And in the last 20 years, the balance of average and wet years to dry years has been completely out of whack compared to what we've seen any time in the 20th century, save for the Dust Bowl period in the late 1920s, early 1930s. We've had 8 average and wet years over the last 22 years, and we now have had 14 dry years over that 22-year period. And that has meant less recharge, less water coming off the mountains in other basins in Northern California, and is a key reason why we're seeing water levels in this region being much lower today than they were 20 years ago. This may continue. We might be in what's called a mega drought. This is a so-called flame graph, which shows the average precipitation for a continuous period of 1, 2, 3, et cetera, up to 30 years. So this is a 30-year moving average in this row. This is a 12-year moving average in this row. And I colored that average. If it is a low precipitation, it's red. If it's high precipitation, it's green. And when you do these, when you stagger these moving averages on top of a timeline, you get these flames in periods that are particularly dry. And the last big flame, and the only large flame we've had in the past, this is from 1896 to 2021. The biggest flame we've had was in the late 1920s, early 1930s. The flame that we've created over the past 20 years now is starting to approximate the size of the flame that we've had in the 1920s and 1930s. If I zoom out and not only show the past 100 years, but show you the past 1200 years, this is the flame that was created by the Dust Bowl. And it is one of the largest flames in the last 1200 years, with even larger flames having indicating large, long mega droughts in the historic record that we've seen here. And we may well be, and there are research papers now out that are saying we are again in a mega drought condition. What that means with respect to recharge and specifically groundwater, we don't know. This is from the recent draft of the Department of Water Resources showing a potential dry, hot, extreme climate for 2100 and the reduction in recharge resulting from that on the order of 30 to 70% throughout much of the state. And this is groundwater recharge. This is not runoff. And it's particularly large in this volcanic region up north, more than 50%, maybe more than 70%. But it could also end up being more, wetter. And some of that's going to have to do with how the ecology adjusts to the change in climate. Are we going to see less ET from the vegetation under a hotter climate with more concentrated rainfall events, or are we seeing more ET? And those are questions that need to be addressed. So I'm going to, as a last example, and it's again an example where we're looking at measurements that can't be done with a meter. I'm looking at the question of nitrate in drinking water. So now we're looking at a groundwater quality question. We've done a ton of work on who is responsible for that nitrate in groundwater. It's primarily agriculture. It's fertilizer use in agriculture. We have and we know management practices that can reduce nitrate loading to groundwater. It's a combination of improved irrigation systems and improved fertilizer management. That has been well documented in many, many publications. What has not been documented very well is how these management practices actually impact groundwater. And the reason for that is that making a groundwater quality measurement in a cropping system is rather difficult. A groundwater monitoring well is a well that's drilled into the subsurface, has a screen that's typically 10 or 20 feet long, right at the water table, and collects water across that 10 or 20 foot screen that may be from 100 to 2,000 feet away, depending on how much recharge occurs and what that regional groundwater flow is. So this well, if I take a water sample from this well, I'm going to see water that's been recharged probably from, it could be only from this area here all the way to this brown area, maybe 100 feet, or it could go all the way to the end of this orchard about 1,000 feet away, less likely from even further away. Moreover, because this is this well has a vertical extent, the shallowmost water is the most recently recharged water. What flows into the monitoring well at the bottom came from furthest away, and it's probably traveled 2 or 3 or maybe even 5 years. So what I'm measuring here when I take a water sample out of here is actually a mixed aged water sample that represents kind of an average water quality in recharge across this source area of the monitoring well. So basically whatever got recharged across this piece here in the last 2 to 5 years. The setting up monitoring systems that actually measure one management practice then means that we have to have that management practice over the entire source area. Typically a half a mile, quarter mile at the very least. And there are very few groundwater monitoring networks like this one that cover a half mile by half mile area. We've had those on dairies. We have this one on an almond orchard, and we now have one with Dr. Kisika at UC Davis in a tomato field. The other piece that we look at is the unsaturated zone and movement of nitrate through the unsaturated zone. Both the unsaturated zone above this black line and the saturated zone below the black line in this 40-foot cross section is highly heterogeneous. And we typically measure when we take samples, we measure them on a small scale. And so they're subject to these heterogeneous outcomes. And as a result, we find highly heterogeneous nitrate concentrations across these profiles. These are 20 profiles in a 150 acre orchard, highly variable from 0 to 100 milligrams per liter, over 100 milligrams per liter of nitrate as nitrogen, with not a whole lot of consistency across these cores. There's not really one particular layer that's particularly high or low. One of the challenges we're trying to figure out with the field research that we're doing is how does that heterogeneity in the unsaturated zone or the heterogeneity of nitrate in groundwater, which also varies over a factor 4 from less than 20 to over 80, how does that relate to how we're managing that orchard and what the nitrogen use efficiency is in that orchard? And interestingly, the losses that we calculate from the orchard based on the amount of nitrogen applied and the amount of nitrogen harvested, so a basic nitrogen mass balance, turns out to be not giving us not a bad idea for how much nitrate we should be expecting in shallow groundwater, which is about 25 pounds per acre, or 25 milligrams per liter, given what we know about management practices in the orchard over the past 5-year period. So we can use this to inform models such as SWOT that can calculate nitrate leaching at the field or subfield scale across very large landscapes, and then couple those with groundwater models that take that loading from the water table and simulate how that loading from the water table then moves through a very heterogeneous subsurface to the wells that are used for irrigation, for drinking water, or domestic wells or public water supply wells. One of the challenges that we're finding here, and I'm going to close with this, is these are very complex models. It's a model run like this, which covers about a 400-year time period. A discretization of this model area, which is about 6 miles by 10 miles and about 1,000 feet deep. This is a discretization discretized into several million tiny little pixels, all of which are used in this simulation. This is a several-hour long simulation on a computer. The question that we're faced with is, how do we use, or how do we design these modeling tools to give us answers on the question how future changes in management practices across the heterogeneous landscape of the Central Valley may impact tens of thousands of wells. In order to do this at this scale, 600 miles by 60 miles, you need different kinds of modeling tools. And so part of what we've developed is meta modeling tools that learn from simulations like this, where we upscale the process, we simplify this process, and put more simplified models into place that we can then operate off of a website, and where on the website, a user can select crops that may have lower loadings, can select how much less loading may come out of those crops, and then within seconds or minutes, see results in terms of how those changes in loading in nitrogen management practice actually impact groundwater in wells, in the county, in the groundwater management zone, in the Tulare Lake Basin, or across the entire Central Valley over the next 100 or 200 years. So again, a modeling tool to do a complex measurement, but fed with a lot of information. The challenge, again, is the outreach and making users comfortable with knowing that this tool can provide consistent results and results that are relevant to the decisions that agricultural users, agricultural coalitions make when addressing the requirements of new regulations. Thank you very much.
Wow, thanks, Thomas. That was quite a ride. Yeah, thank you for taking
I don't know,
the
do
time.
we, yeah,
Yeah, we do have at least, a few minutes since we started, 5 minutes after the.
yeah, and I'd be happy
three.
to stay a little longer.
Yeah, so I'm just going to read the question that we have in the chat. It says, does the BMP loading model incorporates AgMAR practices?
Does the BMP loading model, let me see that. Incorporate AgMAR practices. Yes, so we are working on we're planning to work on a version of this model that will allow, in fact, for looking at AgMAR practices. And we've done some work. Bastani has done his PhD looking at AgMAR in areas near public water supply wells of disadvantaged communities, this being a case study in Ceres near Modesto. This is a blow up of that area. It's their public water supply well. And he used and further developed a mud flow groundwater flow and transport model, actually the flow model, and then added the transport model capacity to it, to identify what the source area is of that public water supply well, and then look at how management practice changes. And it's mostly almond orchards and cornfields, plus some alfalfa. How nitrogen management practice changes in that region could impact in the long run water quality, but also how managed aquifer recharge, if done in this agricultural landscape, could improve water quality conditions in that public water supply well. And it turns out that having AgMAR operations near public water supply wells could be a particularly promising management practice to relatively quickly improve water quality conditions in some of these community wells that are in disadvantaged communities surrounded by agricultural areas.
Okay, the next question is related to the uncertainty that you talked about. And the question is, do you think there is a need to reduce the uncertainty in the model you presented, or other areas more important? Example, more models, grower communication, etc. And the second part is, if reducing uncertainty is important, there is a higher, or is there a higher need, better quantifying individual parameters within a system, relationship between parameters, identifying new parameters? I don't know, this is, I think the question is.
Yeah, I'm looking at the question myself.
Yeah.
So let me answer maybe this way. The important takeaway message here is, no matter how we twist and dial it, these models are going to be somewhat complex. Sometimes to answer some questions, very simple models can be sufficient. Other types of questions, we might need more complexity. What we have spent quite a bit of time on is for the specific question of what practices need to be put in place to comply with California regulations on groundwater nitrate, which basically say in the long run, we need to manage agriculture so that groundwater nitrate can be better than the drinking water limit, better than 10 milligrams per liter. What tools can we develop that can help answer that question? There are groups other than us that actually deal more with the modeling in the Verizon and of the cropping system. The SWAT tool that I've mentioned was developed by a consultant for the agricultural coalitions in the Central Valley, but in collaboration with folks out of Carbon Extension, Isaiah Kisika is part of that, and others. And we're trying to inform models like that with the field research that we're doing. And I know others here are doing field research in this arena as well. informing those models, understanding which uncertainty we can live with because it doesn't make much of an impact on the prediction, and which pieces we need to understand better, do more field research, better understand processes. That's part of this process. The challenge is going to be, one of the perhaps biggest challenges is going to be, as we're starting to employ these models to make decisions on what growers can and cannot do, possibly, we need to first of all build some trust in using that tool to make that decision. But we also need to build expectations to be not that these models never change. We will certainly learn much, and this goes for the nitrate issue, this goes for the salinity issue in groundwater. This also goes for everything that's done around groundwater sustainability plans on the supply side. We will learn a lot over the next 10, 20 years. Our models will improve a lot. And as a result, our decisions will have to change. So thinking of this as an adaptive management process and creating expectations among the users and those that are impacted by the decisions that we make, according to an adaptive management cycle, is really important. We need to all understand that this is adaptive management. We make decisions, we try to monitor better, we learn, we improve the models, we reassess our decisions.
Okay, the last question in the chat is, in the context of Sigma, how will agencies review undesirable situations and which model tools are reliable? Which is kind of related to what you just mentioned.
Yeah. So the undesirable results are primarily, it's about undesirable results and more specifically about what Sigma calls significant and unreasonable undesirable results. That, of course, is a very qualitative statement, and yet Sigma requires a very specific quantitative minimum threshold for water levels, for groundwater storage, for seawater intrusion, for land subsidence, also for surface water depletion. And basically, Sigma tells the GSAs, you determine what your undesirable result is, try to get toward articulating a quantitative value as best as you can, and that's where you set your minimum threshold. There are undesirable results undesirable results are primarily defined by the stakeholders and the water users, but also those that are impacted by the decisions of the GSA. So all the beneficial users, all of the indirect results of that decision. Being expansive on understanding the various undesirable results is important. DWR, the biggest critique of on the existing groundwater sustainability plans, those that had to be submitted by January of last year in the overdrafted basins, all the basins south of Sacramento in the Central Valley, the biggest critique we've heard on those is that most of them ignored identifying outages on domestic wells as an undesirable result. And so a lot of them set their water levels much deeper than they were in 2015 because they needed time to respond to Sigma. They knew that they were continuing to overdraft groundwater and that it would take time to implement projects. And we might have more drought of the kind that we've had over the last 20 years. And so they wanted to provide themselves a buffer to make sure that they can actually meet that minimum threshold. But it would likely mean that there's a lot of domestic well outages. If you set your minimum threshold 50 or 60 or 70 feet lower than where water levels are today, there's going to be a lot of well outages in the meantime. And that's, I think, something, while perhaps some of those GSAs then articulate those as undesirable results, certainly there's communities out there to whom this is a very undesirable result. And DWR does have a responsibility to look out for those broader undesirable results and make sure that those are addressed. It'll be interesting, and it's not articulated. There's not a checklist of undesirable results that DWR has spelled out in the regulations. It'll be interesting to see how they deal with that.
Okay, with that, I just want to be respectful of other people's time. We're already 8 minutes past 4. So I just want to take a moment and say thank you, Thomas. This was a really enlightening talk.
You're welcome.
And
thank you back to everybody taking the time on late Friday afternoon for a talk, another talk on Zoom.
I know, Thomas. Yeah, I know. And then
thanks all for being here.
Yeah,
and reach out to me with more questions if you have any.
Yeah, please do that. And our next water webinar will be on June 18th. Huri Ajami will be talking about groundwater again. So do tune in.
Cool. See you all then.
All
Stay
right.
healthy.
Right,
Thomas, thank you very much. This was very good.
You're welcome.
All right.